In our last major topic on enolates, we will be looking at enolate addition to alpha-beta unsaturated aldehydes and ketones. We've already talked about nucleophilic substitution, nucleophilic addition to aldehydes and ketones, and nucleophilic acyl substitution, primarily adding to esters. Well, we're looking again at nucleophilic addition, but in this case, we are talking about alpha-beta unsaturated aldehydes and ketones. So these might be connected to different things, but with an alpha-beta unsaturated aldehyde and ketone, a nucleophile can add here, or it can add here. So that's what we'll be looking at, and we're going to have a few examples. We'll be starting with the Michael reaction. So here we have an example of an alpha-beta unsaturated aldehyde, and we need to admit that we get a little bit crazy when it comes to naming and numbering because there are particular rules for IUPAC naming of this compound, but then there are other ways that we refer to this. If we focus on the carbonyl, then the position adjacent to the carbonyl is the alpha position, and then this is the beta position. And that has nothing to do with naming. But then when we think about adding to an alpha-beta unsaturated carbonyl, then we use another different system where we call this the 1 position, 2, 3, and 4. Often we will use these terms or these identifiers within the same context. So not quite interchangeably, but mixed together. So looking at an alpha-beta unsaturated aldehyde or ketone, what we need to think about is the fact that this carbon, this carbon, this carbon, and this oxygen are all sp2 hybridized. That means that we have a p orbital, a p orbital, a p orbital, and a p orbital, so we can have an extended pi system. So even though it is drawn as a double bond, single bond, double bond, we know that it exists as a delocalized pi system. So we can think of this in terms of resonance structures. We can draw another resonance structure, and this is true for any aldehyde or ketone. We can imagine that these electrons move onto the oxygen, and that would give us this resonance structure where we have a positive formal charge on the carbon and a negative formal charge on the oxygen. These are the same. But for an alpha-beta unsaturated aldehyde or ketone, we have another resonance structure. We can imagine these electrons move here, leading to this resonance structure. And now we have a positive charge here. So for this compound, our resonance hybrid is going to look like this. We have partial double bond character here, partial double bond character here, partial double bond character here. We have a partial negative on the oxygen, a partial positive on this carbon, and a partial positive on this carbon, which means if this is our 1 position, our carbon at the 2 position, 3, 4, and our carbon at the 4 position both have positive character. Therefore, if a nucleophile comes along, it could potentially add to this carbon or to this carbon. So let's consider the two possibilities. So if we have 1,2 addition, then our nucleophile adds to the carbonyl carbon, pushing these electrons up onto the oxygen. So our alkene isn't changed. Here we have an O-, this H is still here, but now our nucleophile has added. The O- can grab a proton from the solvent, and we end up with this. So our 1,2 addition product, our nucleophile has added directly to the carbonyl carbon, and we end up with an alcohol. And notice our alkene is unchanged. On the other hand, if we have an alpha beta unsaturated aldehyde or ketone that goes through 1,4 addition, then the nucleophile will add here, pushing these electrons here, pushing these electrons onto the oxygen. So we get, as an intermediate, this species where our nucleophile has become connected here. Now, when this intermediate grabs a proton from the solvent, rather than the oxygen grabbing it directly, which would give us an enol, instead, these electrons will fold back in here, pushing these electrons to grab an H from the solvent, for example. And what we end up with is something like this. So here is the additional hydrogen that the intermediate grabbed from the solvent. This is the carbonyl. And then here is where the nucleophile became connected. So overall, it means that a nucleophile and a hydrogen became connected to what used to be the alkene. So with 1,2 addition, our nucleophile added to the carbonyl carbon, and we ended up not changing the alkene, but it was direct addition to the carbonyl. With 1,4 addition, the nucleophile added 1, 2, 3, 4 to the 4 position so that the nucleophile becomes connected here, but our carbonyl is restored and our alkene is no longer present. So with an alpha beta unsaturated aldehyde or ketone, it is possible for them to undergo 1,2 addition or 1,4 addition. The question is, which ones will undergo 1,2 or 1,4? Well, it doesn't really matter on the alpha beta unsaturated aldehyde or ketone. The difference is in the nucleophile. So in general, 1,2 addition is faster. So every nucleophile will do 1,2 addition. In general, the 1,4 addition product is more stable. So anybody is going to do 1,2 addition, but it can equilibrate. So if the reaction goes forward with 1,2 addition, but then it can go back again, it'll restore the original compound, and then we can get 1,4 addition to occur. So whether or not a compound undergoes 1,2 or 1,4 addition is really based on the strength of the nucleophile and whether these reactions are reversible or not. Here are some examples that we may have looked at before. We have an alpha beta unsaturated ketone, and we have 4 different types of nucleophiles. So in our first case, we have a Grignard reagent. Now we know that a Grignard reagent is a really, really strong nucleophile, a really, really strong base. So this is going to add 1, 2. So the methyl group will add here, and these electrons will get pushed up. We will have as an intermediate something that looks like this. And then on aqueous acid workup, this O- can grab a proton, and we end up with this. So it is the 1,2 addition product. In our next example, we are adding cyanide. So cyanide will again add 1,2. So we're going to get something that looks like this, but this is reversible. So this can revert back to our original compound, and then the cyanide can add 1,4. So that would give us our cyanide is connected here. These electrons got pushed here. These electrons got pushed here, right? So when the nitrile adds, then these electrons go here, pushing these electrons up here. And we get this intermediate. And then aqueous acid workup, for example, or else it could just grab a proton from the solvent, and these electrons will come back in here, and these electrons will grab a proton. So our isolated product is going to look like this. So with a very strong base or nucleophile, the reaction is not reversible. So 1,2 addition is going to be the isolated product. With a weaker base, such as a nitrile, this will add 1,2 going through this intermediate, but it can be reversed so that it'll add 1,4, leading to the 1,4 product as the isolated product. If we have an amine as our nucleophile, this will again go through 1,2, but it's a weak enough base that it is reversible, and so this will lead to the 1,4 addition product. I'm not showing all the steps, but this will be our isolated product. And with our last example, we have a lithium dialkyl cuprate. Now, the mechanism is not the same, but we can think of this as if it is a weak base, which means it is a weak nucleophile, which means we're going to get the 1,4 addition products. So what we will end up with is a product that looks like this. So using the cuprates, this is a nice complement to using a Grignard reagent or an organolithium. With a Grignard reagent or organolithium reagent, we're going to get 1,2 addition of some alkyl group. With a cuprate, we are going to get 1,4 addition of an alkyl group. And so they complement each other nicely. So the point is, if we have a very, very strong nucleophile base, then we get 1,2 addition. If we have a weaker nucleophile base, because the 1,2 addition can be reversible, then we end up with the 1,4 addition product. Now, how do we take this forward to consider reactions with enolates? In our first example, let's look at the reaction of acetone with an alpha-beta unsaturated ketone in the presence of hydroxide. Well, the hydroxide could potentially pull off one of these protons, but when that happens, there's nothing else that can happen. If the hydroxide grabs off one of these or one of these are equivalent to each other, then we will get this enolate. So keep in mind the reason why the alpha hydrogens are more acidic than other hydrogens connected to sp3 hybridized carbons is because this enolate is because the conjugate base is stabilized by resonance into the carbonyl. If this one was pulled off, then we can have resonance here, but we have resonance here, and it's kind of like we're resonating in two different directions. So it's not going to be as stabilized, which means this is slightly less acidic than these. Now, once we have this enolate, well, this is now our nucleophile. So the nucleophile will add 1,2 because nucleophiles will always add 1,2 because it's faster. But the real question is whether it will equilibrate to give 1,4 addition. Well, I just mentioned that these hydrogens are more acidic than other hydrogens connected to sp3 hybridized carbons that are not adjacent to a carbonyl. But it's still a relatively weak acid, which means this is a relatively strong base. It's not as strong as a Grignard, but it's definitely stronger than a nitrile. So is it a weak enough base to equilibrate? Let's hold off on that. Okay, this is a problem that we're not ready to solve just yet, but maybe we can avoid the question. So we'll come back to that. Next, let's take a look at this example. Now here we have a beta diketone So these hydrogens are much more acidic than these or these. Therefore, when this mixture is treated with hydroxide, the hydroxide is going to pull off this proton. So what we get will be this enolate, and this enolate will add 1, 2, but because these hydrogens are stronger acids than these hydrogens, for example, that means that the conjugate base is a weaker base. So a weaker base is more likely to be able to equilibrate from the 1,2 to the 1,4 addition. And that's what's observed. So yes, it will go through 1,2, but we're going to focus on when it equilibrates and we get the 1,4 addition. So these electrons can add here, pushing these electrons between the other carbon, pushing these electrons onto the oxygen. So that is going to give us, here is our CH, that was the nucleophile, and that formed a new bond to this carbon, which is a CH2, which is connected to the CH, which is now double bonded to this carbon, which is connected to the CH3, and it is connected to the O minus. Now, when these electrons collapse back down, this pair of electrons can grab a proton from the solvent, right? We're still under basic conditions. So either it is grabbing a proton from solvent or it could be on aqueous workup, but that will lead to this connected to the CH2, CH2, C double bond O, sorry about that, CH3. So we can do 1,4 addition using an enolate as the nucleophile. So conjugate addition or 1,4 addition using a carbon enolate as the nucleophile, this is called the Michael reaction. So focusing on the alpha beta unsaturated ketone, what we have then is the enolate added to the 4 position. So it is conjugate addition or 1,4 addition. Next, let's look at a couple other examples. Okay, so let's take a look at reactions of an alpha beta unsaturated ketone with a beta diketone, with a beta ketoester, or with a beta diester. I'm not going to go through all of the steps, but I encourage you to do so just to get more practice. But with our first example, if we combine these reagents together and we treat it with hydroxide, the hydroxide will grab off a proton here, generating the enolate, which will add to this carbon, pushing these electrons up onto the oxygen. And then when those electrons come back down, then the electrons are going to grab a proton from the solvent, for example, and what we end up with will be this 1,4 addition product. Next, if we carry out the reaction with a beta ketoester, notice this time we are using an alkoxide base to match the ester. So the methoxide can grab off a proton, generating the enolate, which is going to add 1,4, and that is going to lead to the 1,4 addition product. Now, maybe this is the target, but keep in mind when we looked at the acetoacetic ester synthesis and the malonic ester synthesis, we saw that we could take advantage of having a beta dicarbonyl compound, but then we could get rid of one of the carboxylates. So if we were to hydrolyze the ester, now we can do it by step 1, saponification, step 2, acid workup, or we could just do the hydrolysis under acidic conditions. But that is going to hydrolyze the ester to give us this. And then if we heat up this compound, we can lose carbon dioxide. So remember, for decarboxylation, we need to have a carboxylic acid, and then alpha beta to it, we need to have a carbonyl. So what we will end up with here looks like this. So 1,4 addition, but after we have gotten rid of the ester and then got rid of CO2, it's as if we used the acetone enolate and did 1,4 addition. So on the previous slide, we weren't sure whether using the enolate of acetone, whether that would give us 1,2 addition or 1,4 addition. Well, we could do it indirectly because we know that this is a strong enough acid so that the conjugate base is a weak enough base that it would definitely go through conjugate addition. So we don't have to answer the question from the last slide because we have a way around it. And then with our last example, we have a beta diester. And so once again, we're using the alkoxide base that matches the ester. And this is going to deprotonate here, and that will lead to the 1,4 addition product. That will give us this. Maybe this is the final product, or maybe what we want to do then is hydrolyze and then decarboxylate. And in that case, that would give us this as our final product. So in the end, it's as if we took acetic acid and stuck it 1,4 onto this compound. So a Michael addition involves conjugate addition or 1,4 addition of an enolate to an alpha beta unsaturated aldehyde or ketone. Our product could end up as a beta dicarbonyl, and then we still have this other carbonyl. Now that means that we have a lot of other functional groups that we could continue to react. If we're using a beta keto ester or a beta diester, then after the 1,4 addition occurs, it is possible to decarboxylate, hydrolyze the ester, and then decarboxylate to get a compound that looks more like this. So there's a lot of flexibility. Not only are you making carbon-carbon bonds, you know where those carbon-carbon bonds are going to form, but you also have different handles that you can use for additional reactions.